Hello, and welcome to today's webinar on the latest NHTSA-funded research, modeling freeway traffic in a mixed environment, connected and human-driven vehicles. I'm Lisa Patterson. I'll be your moderator for today. I'm the Tech Transfer and Workforce Development Program Manager here at TREC, the Transportation Research and Education Center at Portland State University. TREC leads the federally funded University Transportation Center, NHTSA, the National Institute for Transportation and Communities. NHTSA is one of 5 national centers across the U.S., and our research focus is on improving mobility for people and goods to build strong communities. This Portland State-led partnership includes the University of Oregon, Oregon Institute of Technology, University of Utah, University of Arizona, and the University of Texas at Arlington. Our webinars are based on original research conducted by faculty, researchers, and students at these NHTSA partner universities. Our goal for these webinars is to get useful research results in the hands of practitioners, academics, and stakeholders like yourselves. All right, our speaker today is Dr. Terry Yang from the University of Utah. Terry is an assistant professor in transportation engineering at the University of Utah. He received his PhD and MS degrees in civil engineering from University of Maryland, College Park. His current research areas include traffic operations with connected automated vehicles, evacuation planning and operation, big data applications in transportation, traffic safety, and network flow modeling. His research is sponsored by NSF, US DOT, Utah DOT, MDSHA, which is Maryland State Highway Administration, and his research today is funded by NHTSA. He is a member of TRB Traffic Signal System and Emergency Evacuations Committees. He is also an editorial board member of ASCE Journal of Urban Planning and Development and panelist of NSF and NCHRP. All right, before diving into the webinar, I'll just want to let you know about a few of our upcoming events. On February 1st, we'll have our first Friday Transportation Seminar of 2019. Brianna Orr from the Portland Bureau of Transportation and John MacArthur from TREC will be reporting on the Portland e-scooter experience. You can join us in person at Portland State University or watch online. Our next webinar will be on February 27th with Mark Schlossberg from University of Oregon to discuss their new guide, Rethinking Streets for Bikes, an evidence-based guide for bike-friendly street retrofits. You can also see our full schedule of upcoming events online at trec.pdx.edu/events. And finally, before I hand it over to Terry, I just want to give you an overview of the webinar. So Terry will present for about 40 minutes, and during this time, you can submit questions which will be answered at the end of the webinar. We will be recording today's webinar and we'll make it available on our website, and you'll also receive it in the video recording and presentation slides in an email following the webinar. And if you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. Instructions on how to redeem the credit will also be included in your post-webinar email. During the presentation, you may submit questions for Terry by using the questions pane on your control panel, and we'll track these questions for him to respond to them at the end of the webinar. If we run out of time, we will send out written responses for any questions left unanswered. And with that, I will hand over the presentation to Terry.
All right. Hi, Lisa. Are you able to see my screen right now?
Yes. Yep. We can see your screen. It's not in the full screen setting yet. There it goes.
Okay, cool. So thanks a lot, Lisa, for the introduction, and good morning for the people from West and Midwest, and good afternoon for the people from the Eastern Coast. Today I'm gonna present some of our work related to modeling the freeway traffic in the mixed environment, which means we have both connected and human-driven vehicles on the road. So this is a joint work with my master student, Zhehao Zhang, and my PhD student, Alan Zhang, both of them from the University of Utah for sure. So firstly, I want to briefly talk about the definition of the automated vehicles, for short is AVs. So the automated vehicles are operated with the support of different vehicle automation functions, which definitely relies on the real-time sensor data for making the maneuver decisions. So here the maneuver decision including acceleration, deceleration, and lane changing behaviors. And so the US DOT provide the definition of 6 levels of vehicle automation, and I'm pretty sure a lot of people have been familiar with this table. And so definitely without any automation function, that would be defined as the level 0, and with a fully automation function, that would be level 5. And right now, for most automated vehicle has been put on the market, it will be around level 3. But I just got the news a few days ago saying that Waymo has announced that they're going to started to produce level 4 automated vehicles. And for the following slides, I want to talk about the difference between autonomous vehicle and automated vehicles. I'm pretty sure everyone heard this kind of terminology, including automated vehicles, autonomous vehicles, driverless car, self-driving car. So all of those terms sounds pretty similar to each other. And even for me, I have been confused by those terms for a long time. But technically, there's definitely some slightly difference among those terminologies. And the first one, we want to look at the main difference between the automated vehicle and autonomous vehicle. So in terms of definition, an autonomous vehicle is a car that is capable of sensing its environment and navigating without human input. So we can consider like the level 5 vehicle automation would be considered as autonomous vehicle. And there's a Nissan engineer comments about the autonomous vehicle, saying that a true autonomous vehicle would be the one where you request it to take you to work, and then it decides to go to the beach instead. So definitely that is a joking, but if we want to see that more plainly, so that would be a truly autonomous car would decide on destination and the routing plan, as well as the control within the lanes. And an automated car would only follow the order about destination and route, and may only adopt some lane keeping or car following guidance. So from those comments, we can definitely see the difference between the automated vehicle and autonomous vehicles. And here it is, our future car will definitely be the autonomous vehicle, and everyone can just sit in the car, and you can just set up your destination, and then you can just enjoy the life in the car. You can do whatever you want. You can watch a movie, you can read a book, you can even attend a webinar in the autonomous vehicles. But definitely, we still have a long way to go to achieve the autonomous vehicles. So the conclusion is a car that can navigate the lanes or traffic or mind speed limits is technically an automated vehicle, definitely not an autonomous vehicle. And the next difference we want to discuss is about the self-driving and driverless cars. So self-driving car is kind of a term Auto Trader used to encompass the entire idea of car doing some of the work of moving a car from point to point. So it is a more general and inclusive term. So in other words, we could say the automated vehicle would be considered as a self-driving car, but the driverless car would be something similar to autonomous vehicle. So that would be totally operate the vehicle without a human input. And definitely all driverless cars will be self-driving, but all self-driving cars are not driverless. So that is similar to the difference between the autonomous vehicle and automated vehicle. All right. So now let's briefly look at the one of the most famous automated vehicles on the roads is the Tesla automated vehicles. So we have a couple of Tesla in our university, and we have been testing using the Tesla vehicle to study the driver behaviors, and that is mainly led by the psychology department in our university. So in terms of the vehicle automation in Tesla, there are two important control factors that can be set by the drivers. The first one is the desired speed, and the second one is the minimum following gap. So when the vehicle are operated on the road, firstly, the vehicle will intend to drive at the desired speed, let's say 50 miles per hour or 60 miles per hour on the freeway. And then if there is some vehicle in front of the Tesla vehicle, and if that vehicle is driving at a slower speed, let's say 50 miles per hour, and then the Tesla will automatically choose to slow down and to follow that vehicle in front, and with but definitely maintaining the minimum following gap. And so that is the typically operational logic of the current automated vehicles. And in most model of the Tesla, they don't provide the automatic lane changing function, but they can definitely provide some lane changing supporting system. But still, the driver, the human, has to make the lane changing decision. And we have also been using the Tesla to test the driving on the local roadways, which involves the signalized intersections. And at that point, if there's a vehicle in front of you stop at the red signal light, the Tesla will totally be fine by following that vehicle. But if the Tesla turns out to be the first vehicle in the queue, then because of the lack of connectivity technology, the Tesla will not be able to recognize the traffic signal. So in that case, the driver has to push the brake by themselves instead of allowing the vehicle to do that. And now let's move to another path of the smart vehicle technology, which is connected vehicles. So I host a workshop in San Francisco about 2 years ago, and we invite people from those startup company who has been developing the autonomous vehicle for a long time, and also definitely some other people who has been working on connected vehicle technology, both from university and the government. And the interesting is a lot of autonomous vehicle company, they never heard about the term connected vehicles, and that is the first time they learned the terminology of connected vehicles. But we definitely have observed the necessary of merging these two technology together, including both automated vehicle technology and connected vehicle technology. So in terms of the connectivity technology, there's a bunch of communication technology we can use to achieve that, including the DSRC and C-V2X, 5G DMB, and so on and so forth. And right now, the DSRC turns to be one of the most popular communication technology in the US. And about 2 or 3 years ago, the US DOT tends to make the DSRC as the standard of connected vehicles. But that order has been failed after the discussion, because other companies like Qualcomm, they intend to use the CV2X, which is a much newer communication technology. And right now, the DSRC and the CV2X have both of them has their own market share in the US. And the bad thing is these two are not open to communicate with each other. For example, if we have a one connected vehicle which is with the DSRC equipment, the other is with CV2X, unfortunately, these two vehicles are not be able to talk with each other. But the CV2X has some advantage over DSRC when the time of 5G comes, and that will have a much shorter communication delays compared with the DSRC. And with the connectivity technology, the connected vehicle will be able to talk with each other, and then that refers to vehicle-to-vehicle communication, and also talk with the infrastructure. So that will be V2I communication. And definitely we have all the other communication like V2P, vehicle to pedestrian, and V2B, vehicle to bus. And to mention that in Salt Lake City, the Utah Department of Transportation are operating a connected vehicle corridor on the Redwood Road. So that includes 30 intersections, and all of them are installed with DSRC communication device, the roadside unit RSU, and they also installed the communication device OBU, the onboard unit on the buses. And currently, the connected vehicle application is bus transit signal priority control. All right, so now if we merge the connectivity technology along with the vehicle automation function, so that will give us the connected automated vehicles. So the connectivity technology will allow the exchange of traffic information between the vehicles and infrastructure. And the vehicle automation function will automatically adjust the speed in real time according to the desired speed and distance to the vehicle ahead. So basically, for our future car, the control logic is the sensor on the vehicle will provide the driving environment information. Then, along with the connectivity, we'll gather information from the other vehicles. Then, the vehicle will be able to provide both warning function and control function. So in terms of the control, right now, basically will be the speed, acceleration rate, deceleration rate, and warning will be the lane changing support function when the driver decides to make lane changing behaviors. And now with the connected automated vehicle, for short is CAV, we want to briefly talk about the CAV operational environment. So the CAV are typically equipped with communication devices, for example, the DSRC or the CV2X, as we just discussed, and also the onboard sensors. So right now there will be 3 different type of sensors being implemented to support the vehicle automation functions, including the radar sensor, the LiDAR sensor, and camera sensors. And among these 3 sensors, the LiDAR sensor provides the most reliable information, but definitely that is one of the most expensive sensor that has been used on the connected automated vehicles. And the camera sensor is much cheaper, but it also has a lot of limitations in terms of the light condition and also the visibility of the road. And Tesla is one of the automated vehicle that relies on the camera sensors, and because their CEO believed that the camera can do as good as the human drivers. As long as the human driver can be able to observe what happens outside, the camera sensor will be able to do the same thing. The radar sensor is not that expensive, but the detection error is usually much larger than the LiDAR sensor. So in most cases, the radar sensor are used as a supplemental detection function to support LiDAR sensor and camera sensors. So in the next probably 10 to 20 years, we can still expect that the connected automated vehicle will be sharing the road with the regular vehicle, or in this study we call it human-driven vehicles. So in the figure we can see that we have the red one to be the CAVs and the blue one to be the human-driven vehicles or regular vehicles, and with the communication device and the CAV will be able to talk with each other and also get the information from the communication infrastructure. Usually will be the roadside unit, and also the detection function on the CAV will be able to detect the existence of other human-driven vehicles and also may help the vehicle automation function to make the maneuver decisions. So that would be the typically operational environment, which is also, as we mentioned, would be a mixed environment that includes both CAV and HVs on the road. And with the CAV technology, here are a few popular CAV applications on the freeways. So definitely on the signalizing section, we have other applications such as speed, green speed control and signal traffic signal light optimization with a connected automated vehicle, or the transit signal priority as the Utah State are doing right now. But in this project, we're mainly focused on the CAV applications on the freeways. So the first application is called cooperative adaptive cruise control. for short is CACC, and that is also one of the favorite of USDOT, and they have been putting a lot of efforts on testing the CACC on the freeways. And the logic is we have a bunch of connected automated vehicles, and with a V2V communication technology, and they can be able to follow with each other and to form a platoon of vehicles on the freeway. Then in that case, we can allow much shorter gap between those connected automated vehicles, and definitely by doing so, we can help to save reduce the traffic congestion condition, and also improve the roadway capacity, because we have a much shorter gap between the vehicles. And also because we have the vehicle CAVs follows each other, then the fuel or energy consumption will be reduced for the following vehicles, because they have much smaller air resistance when they are driving on the road. And in terms of the operation of the CACC applications, they can be either operated on a managed lane, for example, similar to the concept of using HOV or HOT on the freeway, or they can be operated on the lanes, and that will be definitely shared with the human-driven vehicles. So in the review of the literature, there will definitely both the type of operations in the has been started by researchers, and the USDOT, along with the company, the Leidos company, I remember they have been testing some CACC applications in the field test. So the next application is a speed harmonization. So the speed harmonization is a method to reduce congestion and improve traffic performance when there is a point or there's a lane, because of the lane merging or bottleneck that create a downstream a slow speed zone. Then the speed harmonization will somehow gradually lower the speed before a heavily congested area in order to reduce the impact of shockwave, and also to eliminate the stop and go traffic condition, and definitely also reduce the frequency of potential crashes. And the basic logic is with some traffic speed control optimization function, then through the vehicle to infrastructure communication, the system will be able to provide the advisory speed to the connected vehicles, so that if that is only human-driven connected vehicles, in most cases that will be provided through the advisory speed suggestions. And if that is a connected automated vehicles, definitely the vehicle will automatically follow the desired speed. And the speed harmonization can be applied to either individual connected vehicles or the connected vehicle platoons on the freeway. So which you can observe from the figure on the right hand side. So we can provide the information to both individual connected vehicles or the platoons. Then all the vehicle will follow the speed, and then hopefully we can slow down the traffic and before they reaching the congested area, then to smooth the speed reduction process, and also eliminate the mitigate the impact of the shockwave. All right, so I think the concept of speed harmonization is definitely not new, because there's a very similar concept called variable speed limit control, which has been implemented for long periods. And so basically the variable speed limit control is we provide the advisory speed to the drivers. And originally, the variable speed limit has been implemented to improve the roadway safety performance under hazard weather condition. Like we got snow, we got ice on the road, and we provide much slower speed limits to the drivers. But later on, researchers and engineers observed that the variable speed limit can also be implemented to mitigate traffic congestion when we have a downstream bottleneck. So here is an example of implementing the variable speed limit in Maryland, which we have been conducted a field study about 4 years ago. So it's on the MD100 near the Coca-Cola Drive. Usually we can observe a lot of traffic congestion on the downstream side because we got a lot of traffic coming from the on ramps. Then we place two variable speed limit sign on the freeway to somehow slow down the traffic before they reaching the downstream bottleneck. So by doing so, we can smooth the traffic speed reduction process and then prevent the stop and go condition. So definitely that would be very similar to the speed harmonization with connected vehicles, but the difference is the first one is by providing advisory speed via the vehicle to infrastructure communication channel. The other one is to provide advisory speed to all of the drivers with the variable speed limit sign. And in some other country like Germany, they also implement the variable speed limit control on the freeway, but they allow different speed limit on different lanes. But in the US, in most cases, we just provide the same speed for all the lanes on the freeway. So before we move to the modeling of traffic state under the connected vehicle environment, I want to briefly talk about the variable speed limit control logic. So basically, we can have the firstly, we usually divide the speed in the freeway into a bunch of sub-segment, and we put the variable speed limit sign there, and we put detectors to gather the real-time traffic information. Then we rely on a traffic flow model, which be able to tell us what would be the corresponding travel time or travel delay or throughput, given the different value of variable speed limit sign. So based on that logic, then we can later on produce the optimal speed to the drivers. And so that would be basically variable speed limit control logic. And definitely we can observe that the effectiveness and efficiency of the variable speed limit control will definitely rely on the accuracy of the traffic flow model. So how you measure the traffic, how you estimate the traffic state, given the information from the detectors. Because in most cases, we only place a bunch of detectors on the freeway. For example, we put a upstream detector to gather the inflow, and we place a downstream detector to get the outflow, and we may or may not put some detector between the upstream and downstream detectors. And sometimes we also put detector on the on-ramp and off-ramp to gather the on-ramp flow and off-ramp exiting flow. So we have very limited number of detectors has been implemented. So definitely we need a traffic state model that can help us to estimate the traffic state performance over the entire freeway segment. And because we want to do the real-time optimization, so we definitely need a very efficient traffic state model. So in terms of the traffic estimation, there were three levels of models, including the macroscopic level, mesoscopic level, and microscopic level. So in this case, we will definitely use the macroscopic level, which is the most efficient model for the real-time operations and optimizations. For the mesoscopic, usually we use that for the traffic assignment analysis or the large size network simulation. And for the microscope simulation, I believe most of you are familiar with those software like vSim, CoreSim, and MSIM. They're basically microscopic simulation models. But for the microscopic simulation model, usually we cannot use that for real-time optimization. Instead, we're using that for system evaluation. So here we're going to use the macroscopic traffic flow model to support the variable speed limit. And then also we borrow that idea back to the traffic state estimation under the mixed environment, including connected vehicles and human-driven vehicles. So now let's briefly talk about the macroscopic traffic flow model. So the traffic state estimation has long been identified as an important task within the traffic control loop. And as we mentioned, reliable traffic flow estimation is the foundation of many good traffic management strategies, including the variable speed limit control, the speed harmonization with connected vehicles, and also the RAM metering control. And under the mixed traffic environment, which including both CAV and HV, the CAV can definitely affect the whole freeway traffic state by changing their motion state, because CAVs are sharing the speed, sharing the road with the human-driven vehicles. Now, let's briefly talk about the conventional macroscopic traffic flow model, which is also the second order traffic flow model. So to analyze or estimate the traffic state on the freeway, as we mentioned, in most cases, we're going to divide the freeway segment into a bunch of subsegments. And in most cases, the length of each segment will be around either 500 meters or a half mile, and we cannot put the segment length too short, because we don't want the vehicle will jump from one segment to another during the study interval. Usually the simulation interval would be like every 10 seconds. So for example, we don't want the traffic to travel from segment 1 to segment 3 and totally pass the segment 2 during that 10 seconds. So that's why in most cases we set the length of the segment to be half mile or 500 meters. And in each subsegment, we are particularly interested in the three factors, including the flow rate that we're leaving the that segment. Here we use the QIK to represent that, and also the density, in terms of the number of vehicles within that segment, and also the mean speed. So here the mean speed will refers to the space mean speed. So we'll be interested on estimating these three factors within each segment. And the conventional macroscopic traffic model will be like this way. So the first equation is to update the density from k time step to k plus 1 time step. So basically we based on the number of vehicle coming in and number of vehicle getting out, and plus the current number of vehicle inside. Then we can estimate the number of vehicle in the next time step. And the next equation is the one used to estimate the mean speed. I don't want to go to the detail of this equation, but the logic would be similar to the density function. So we rely on the density and speed from the last time step. Then we use that to estimate the speed in the following step. Then we have a fundamental diagram relationship to estimate the flow based on the density and the speed. So basically the flow will equals the density times the speed. Then that provide us the flow information. So with these three equation, we can somehow estimate the traffic state on the freeway segment. And for those detectors that placed on the freeway, that will provide us the Q information and the R and S, which is the on-ramp and off-ramp information. And now let's talk about the mixed traffic flow pattern. So as we mentioned, there will be a bunch of CAV applications such as CACC cooperative connected automated CACC cooperative adaptive cruise control and the speed harmonization. So in those applications, those CAVs will be operated with different speeds compared with the HVs, because they're getting the advisory speed from the infrastructure. And then we can expect that the speed change or optimization of CAVs will be definitely affect the speed of the HVs, because they are sharing the road. And let's look at this figure, which is the summary of our simulation study. So we have the case 1 is a simulation with both CAV and HVs, and the second case 2, is the case with only human-driven vehicles. So there's no speed control has been implemented on any vehicles, even without variable speed limit control. So on the first case, we place the speed optimization, speed control on the CAVs, which will be the red dots over here, then we can observe that we're providing the smaller speed to the CAVs compared with the blue cross, which is the same case but without speed control. But if we look at the brown triangle over here, which is the average speed of the HVs, we can observe that compared to case 1 and case 2, even for the HVs, they don't receiving any advisory speed from the infrastructure, but somehow they have slowed down a little bit compared with the case without CAV. So from this simulation, we can observe that if we place the speed control for the CAVs at the same time, we'll be able to affect the speed of the HVs because they're sharing with each other. So that can be explained from the figure on the right hand side. So for example, we have the green one to be the CAV and the blue one to be the HV, and this is the flow direction. And so as the HV and CAV are sharing the road with each other, and when we place the speed control, in most cases that would be a slower speed on the CAVs. Then in some case, the blue car, those HV will have to follow the green car, the CAVs on the road, or they would decide to make lane changing behavior to avoid following a slow vehicle on the road. So we can observe both cases here. The first one is the HV will follow the CAV. In that case, the HV will have the same or similar speed as the CAVs. The other one is the following the vehicle the HV behind the CAV decide to make lane changing to avoid following the slower CAV in the road. So because of this one, we can expect that the CAV will definitely have some speed impact on HV, but such impact should be related to firstly the number of CAVs on the road. So in other words, that would be the penetration rate of CAVs. The second one is related to the flow rate. For example, in the bottom figure, we can observe that the entire road is so congested, and in that case, the HV has no choice but to follow the CAV because there's no available gap for them to make lane changing behaviors. So in that case, we can definitely imagine under this extremity case, the CAV impact will be 100% because no HV will be able to make lane changing behaviors. All right, so to consider this CAV impact and also to fully capture the speed difference between the CAV and HVs, and we somehow come out a different macroscopic traffic flow model under such mixed traffic pattern. So basically, we use different equations to represent the speed for HV group and CAV group. So the CAV group speed formulation would be very similar to the conventional model, but for the HV speed group, we have one additional term here, and here the beta IK represent the CAV impact factor, so CAV speed impact factor, which will be consider the difference between the CAV speed and HV speed. And as we mentioned, here the CAV impact factor will be a very important factor that will affecting the estimation accuracy of the HV speed. And to try in this study, we're trying to somehow capture the value of the beta, the impact factor through from the microscopic level simulation. And in this case, the first case when the blue car, the HV, are following a CAV behind a CAV, the car can be able to either make lane change to left lane or the right hand side lane. But on the second case, they have only one option, is to make lane changing to the middle lane. So that is typically lane changing behavior that can be happen to the HVs when they are behind the CAV. So to estimating the initial value of the beta, the CAV impact factor, we consider the probability of occurring two types of events. The first one is event A, the HV behind the CAV on the lane. And event B will be the HV decide to make lane changing behavior to pass the CAV instead of following CAV in the traffic stream. And for both events, we can use a car following model and lane changing model to represent the relationship here. And here is how we come out the initial value for the CAV impact factor beta. So this is the speed equation for the HV group, and we define the FU to represent the entire term in the speed equation for simplicity, and then we can rewrite the equation to come out the beta based on the value of those factors. And among all of them, among all the factors here, FU is given from the last step, and this term is given from the last time step K. The only unknown variable would be the speed of the HV group in the K+1 time step. And as we mentioned, for this unknown parameter, we use the probability model to consider the happening of these two events, then come out the average speed of the HV under the CAV impact. Then we can use that to estimate the initial value of beta. And as you may notice, there is a lot of assumptions on estimating the value of a beta function, and that's why we may observe the estimation of the beta may not be accurate enough. Then later on that will be affecting our estimation accuracy. So here we want to use the online learning technique. It's called common filter to help us to update those parameters. So basically, the logic is we may place a bunch of detectors on the road that will be able to provide us some real-time measurement, including the speed and flow rate at those detection stations. And also, we can gather the CAV trajectory data from the V2I communication. So then we can use the measurement to help us to update the entire traffic state estimation with the common filter technique. So for those of you who are not familiar with common filter, that is basically a mathematical tool that can help us to update the entire estimate with the limited number of measurements. So for example, we can update 20 estimates with only like 1 or 2 measurements. Okay, so now let's move to the last part, will be our simulation analysis. And we select one freeway segment in Salt Lake City on the I-15. So the entire freeway is with 4 kilometer long, and we divide that entire freeway into 8 subsegments from segment 1 to segment 8, and this will be the flow direction. And also we collect the inflow information and the on-ramp flow information from the PAMS database operated by UDOT. And since we want to somehow simulate the traffic condition under the mixed traffic flow pattern, and in that case, we expect that the CAV will be operated with different speed compared with the HVs. So here we come out an optimization model to optimize the CAV desired speed profile following the logic of speed harmonization. So here the objective function is to minimize the total travel delay, the total travel time along this freeway segment, and the output will be the desired speed of the CAVs on every subsegment along the freeway. And this function will be able to generate totally different speed profile for the CAVs, which will be definitely different from the human-driven vehicles. And to evaluate the accuracy of the proposed macroscopic traffic flow model, we consider 2 different scenarios and 2 different models. The first model is the one without the extended common filter, and the second one is the one with the extended common filter. We didn't put the comparison with the conventional macroscopic traffic model here because the result is really bad. So we only provide a comparison between these 2 models. And here is the first result to showing the speed estimation on different segments. And we have the blue dashed line represent the ground truth, and which directly obtained from the simulation. And the red one represents a model without common filter, and the yellow one is a model with extended common filter. So we can observe that on all the segments we present here, especially the downstream segment, with the although our original model cannot be able to capture the speed, the sudden speed reduction on the bottleneck, but with the common filter, we can somehow improve the accuracy a lot. So here you can observe the yellow line is somehow between the blue line and the red line. And similarly, we can observe that for the flow estimation, the model with extended common filter can provide a really good estimation of the flow compared with the one without extended common filter, especially when for the segment with a lot of flow fluctuation. The model intend to provide a very smooth estimation, but the extended common filter can help us to correct the estimation and also generate this kind of fluctuated pattern in terms of the flow estimation. And here is a table to summarize the estimation errors, including the root mean square error, the mean absolute percentage error, and the mean space percentage error, and by different model. The first table showing the one without extended common filter, and second one showing the one with extended common filter. So by comparing these two tables, we can observe that the one with extended common filter can definitely produce a very reliable estimation of the traffic state. And the last part, we want to conduct some sensitivity analysis, and we want to study the CAV speed impact under different scenarios. Here, we consider different demand level and different CAV penetration rate, and definitely different CAV flows. And in this case, we consider there'll be two lanes on the freeway. And here is a summary of the results here. And here this x-axis is a CAV penetration rate, and this y-axis is demand level, and this z-axis is the reduced average travel time along the freeway segment. And for every case, we can observe that, for example, let's take the case with 150 demand level. We can observe that somehow when we have the when we have the penetration rate of CAV above 55%, then the efficiency of the system will be increased a lot. And in this case, we name this to be a critical CAV penetration rate. And from this 3D figure, we can observe that for a different level, definitely the critical CAV penetration rate will be different. The trend is with lower speed demand level, the critical rate intends to be high, but with a high demand level, the critical rate intends to be low compared with the others. So here are the conclusions. So the new macroscopic traffic flow model can better capture the operational difference between the CAVs and HVs, and also we introduce a CAV speed impact factor beta to somehow estimate the speed impact from CAVs to the human vehicle group. And also the extended common filter can be used to help improving the traffic state estimation accuracy. And the model can also be used for producing the optimal desired speed of CAVs to support the different CAV applications, such as the CACC or speed harmonization. Here is another application of the model we use to support the eco-driving system design for the connected automated vehicles. So basically, this model has two different levels. The planning level, which aims to produce the desired speed profile that help minimize the fuel consumption of the connected automated vehicles. And second operation level is the one in response to the real traffic condition. So you can observe that the proposed model can be used to produce the desired speed profile, which aims to minimizing the travel time. Then based on that speed profile, we can use that to regenerate another speed profile, but with one additional optimization function, which aims to minimize the fuel consumption. So that this will be the desired speed of the CAVs. Later on in real-time operational environment, definitely the speed of adaptation function will be used to change the speed in real time similar to Tesla. We will need to maintain the minimum flooring gap with the other vehicles on the freeway. So then we can observe some fluctuation of the speed in the real-time operation. So this is just an application of the proposed macroscopic traffic model for supporting the eco-driving system optimization. So here, this part will be the one using the proposed macroscopic traffic model, and we have one research paper that has been submitted to IEEE transaction on ITS to describe the entire system. All right, so this is the last slide. We want to acknowledge the support of the niche, and this study is supported by a small start project. Although it's a kind of small research fund, but it provides us a really good start. And I use the project to support one of my master student, Mr. Zhehao Jiang, and he's also this is also briefly his master thesis work. And also Alan Zhang, one of my PhD students, has been helping with organizing the materials and also testing the simulation models. All right, that's it. And I would be happy to answer any questions raised here.
Great. Thank you so much, Terry. For those viewing the webinar, please feel free to continue to submit your questions if you have them. We do have a couple questions already from the audience, though, so we'll go ahead and start with those. The first question refers to a flowchart on slide 13, Terry, and they ask, how were the CAV features considered?
You'll be 13, okay.
13, sorry.
Okay. So this one is not the flow chart for CAV speed harmonization. It's just an overview of a very similar concept that is variable speed limit control. So in this flow chart, we don't really consider the connected automated vehicles, but instead we consider we're providing the variable speed limit to all the traffic. But definitely in real-time operation, we can consider there will be some vehicle that will be willing to follow the variable speed, but some other may not. So still we have the compliance rate of the speed limit in this study. So that would be similar to the speed harmonization under the mixed traffic pattern.
Mm-hmm. Okay. And a question on the model with the EKF matched to the ground truth, mentioning that the results matched very well. Is there a chance that this data may have been overfit the data?
So there's no kind of overfit here. So it's different to the other machine learning technique like regression or support vector machine. So here it's like a real-time estimation correction. So at every time step we have estimate, let's say 50 miles per hour, and we have the ground truth to be 63. Then for the real-time correction, somehow the extended common filter, the EKF, will help us to somehow change the estimate from 50 miles per hour to, for example, 58, which would be much closer to the ground truth. So there's no really overfitting issues here, because we're not going to use the estimate to model the other traffic condition. We'll only use the estimate for the specific case. So that would be like a kind of a real-time correction in response to the reality.
Okay. And then a follow-up question was asked, how many days of data or ground truth have you compared the model to?
So in this study, we only pick up 1 day data for, it's actually not even 1 day, it's like 2 hours of, it's actually 350 minutes data for comparison.
Okay. And then, so those that are still listening, we still have a few more minutes for questions. So please still send them in. I will go ahead. I have a couple questions while we wait for any additional questions from the audience. In one of the earlier slides, you talk about the different automation levels.
Mm-hmm.
And yeah. I was curious. It seems like you said that level 3 is where this work is kind of focusing. And I was curious if you knew any projections on penetration rates for these types of vehicles, using that Tesla as an example.
Currently, the pension rate would be really, really low. I think definitely that would be less than 1% on the road. But people were expecting that in the future, there will be definitely more automated vehicle be appeared on the road, especially with the development of those sensoring technology. The price of the vehicle will be reduced a lot. In that
Hmm.
case, maybe most people will be able to afford automated vehicles. But currently, those automated vehicles are really expensive, and that's why the current pension rate is really, really low at this moment.
Hmm. Great. Great. And then one more question then, and we can, like I said, we can wait a few more minutes if there's any additional questions from the audience. But with this research, you had mentioned it was a small start, and so it's starting this research, getting a really great start. Where do you see your future research building on this?
So actually, right now, well, we have been using the model as a base to study one of uh, the CAV application I talked about here is the CACC, the cooperative adaptive cruise control, and I have one of my students working on this issue, and also we have one engineer from Lido's Income who is helping us to reshape our control framework because they have a lot of experience on implementing the CACC on the freeway. And so right now we're working on a control model to form the CACC platoon and also to control the platoon on the freeway.
Great. And have you been working with any agencies with these modeling capabilities to impact their planning?
I have a one UDOT project from the planning group. They're really interested on starting the benefit of the CAV applications and also look at how the CAV can be affecting their traditional transportation planning. So in that case, we in that project we mainly focus on studying the benefit and cost of implementing different CAV applications. And also I have another project with UDOT is to provide supporting control algorithm for the Redwood Road connected vehicle corridor application. But that one is on the local roadway. The first one is mainly focused on freeway.
Oh, great. That's very interesting. Looks like we had another question come in from the audience. What software are you using to do this modeling?
We basically use Python and MATLAB to do the modeling part, and later on we do the coding in vSim to try to capture the information from vSim. And then later on we use that to compare with our model. But basically, most of the modeling part would be are did in MATLAB.
Hmm. Great. Well, thank you again so much, Terry. It looks like we are close to 11 and there aren't any more questions. So we will go ahead and end the webinar now. But thank you everyone for joining us today. You can view our other professional development offerings on our website at trek.pdx.edu. Enjoy the rest of your day. Thanks everyone, and thanks again, Terry.
Thanks a lot, Lisa, and thanks everyone.